Okay, so we're supposed to find the differential equation governing this mechanical system. It says to draw the force, voltage, and force current analogous circuit. So the differential equation, let us start with mass M1. For mass M1, acting on it, first of all, is F of t. Next force acting on it is, oh, I cut it off, FV1. The next force acting on it is actually a damper here. Sorry, it was cut off. B1. This damper opposes the motion. The motion is going in this direction, so the damper is going to oppose the motion in this direction. So it's going to be B1 times velocity V1. In this case, you can write the x dt, but I'll just rather represent velocity as x dot and accelerations as x dot dot, and then displacement as displacement. This is one. Now the next thing that opposes the motion is the spring and the damper. As the mass is pushing on them in this direction, they'll be trying to push the mass back to its original position. So we're going to have them going in this direction. K1, well, K1 is in between this the displacement of M1 and displacement of M2, so it will be X1 minus X2. We are starting with X1 because we are working in reference to the displacements using X1. The next is the damper force. The damper force is B1 to x dot, that's velocity 1 minus velocity 2, because it's in between the two masses. Next is that the mass itself opposes its own motion. So in this direction, m1 x dot dot 1. So when you write out the full equation, you're going to have this. It's sum of applied forces is equal to sum of opposing forces. So basically, all of them that are facing in this opposite direction, you put them to one side and the applied force on the other side, and then we simply collect like terms, and this is our answer. This is our first differential equation. And for the second differential equation, we're going to consider the mass m2. So for the mass m2, when m2 is displaced by displacement of x2, the damper force b2 is going to try and oppose this motion. So the motion is in this direction, so the damper is trying to oppose it, trying to push it back. So it will be b2 x2 x dot 2. The spring will also be trying to oppose the motion x2, and then the damping force here, as mass m2 is pulling away, they are trying to pull mass m2 back to its original position. So they'll be going in this direction k1, but since it's between x2 and x1, to be x2 minus x1, and because we're dealing with displacement, so displacement by x2, so that's why x2 is starting, and then to be b1 to x2 minus x1 dot dot, because this is velocity, and then the mass opposes its own motion as well. Motion is in this direction, so it opposes its own motion as well. This will be mass m2 x2 dot dot. Now if I write that, the differential equation is going to be, so this is going to be the differential equation. You can see in this case there's no applied force, all the forces are in this direction, in the opposing direction. So applied force is going to be 0. So these are the two differential equations. Now let's go to the force voltage force current analogous circuit. So for force voltage circuit, right, mass is going to become M1 is going to become inductor, M2 is going to become inductor 2. The force that was applied will become voltage. The spring B1, the damper will become resistance. The spring K2 will become 1 over C, and spring K1 1 over C1, so it will be C2. The damper B1 to become resistor 1 2, and damper 2 will become R2. So now this thing has to do with what is sharing the same velocity, right? If I write this from now in terms of velocity, you're going to have m1 So you can see as I've written it in terms of velocity, the integral velocity is distance and the differentiation of velocity is acceleration. In this case, you can see it. You can see that M1, B1, and then F of t, they share the same velocity. F of t is literally the one causing the velocity V1. So if they have the same velocity for a force voltage analogous system, put them in series. So this mass, damper, and F of t will be in series. So the voltage source, we can call it E of t. If you call it V of t, it can get confusing because some may mistaken for velocity. So and then the mass, which is L1, the mass is L1, and then the damper is resistor, which will become R1. Now let's leave this one for now. We'll do it after. And now the same thing for M2. If I bring this formula out, you will see that you can write in terms of M2. So you can see that the mass M1, B2, and K2 are sharing the same velocity. So let's just draw it in a circuit. Oh, I forgot to mention, for force voltage, you're drawing a mesh current, right? So the number of masses determine how many meshes you're going to have. So this is one mesh. The velocity translates to current. So this is V1 and this is V2 because velocity 1 and velocity 2 right here. This is going to be I2. This is going to be I1T. Now the second mesh, I'll leave here for now empty, but I'll draw it after. So the mass M1 is going to be L2, right? The next one is B2, which is going to be a resistor, and then the last one is the spring K, which is going to become a capacitor C2. Now for this particular one, they are in between two meshes, so they have to be here in between the meshes. However, you can see they share the same velocity V2 minus, oh sorry, it's supposed to be V2 minus V1. You can see they share that difference in velocity, and because they share the same velocity, we're going to put them in series to each other. So they're in between meshes in series to each other. This is going to be R12, and then this is going to be, I believe, C1. So that's for false voltage. Now for false current analogy, now for this particular one, you can see the conversions here. And this is node voltage, so the number of masses determine how many nodes you're going to have. So in this case, we're going to have two nodes. Let's call it V1 and V2. I know it's a bit confusing, but manage with me. So same, if you have the same velocity, if you share the same velocity from the formula that we saw, put it in parallel this time, not series. So we know that this and the damper B1 here, we're sharing the same velocity, right? So put them in series. It's going to be current I T in parallel with the M1, which is now capacitor C1, in parallel with the damper B1, which is now R1. And then it's going to connect to this node, the first node. So the first node is basically mass one. So all of this is at that mass one. Now in between the nodes we have this. Remember that these two share the same velocity, right? But in this case we put them parallel to each other and they're in between the two nodes. We put them parallel to each other. So for K1 is going to become an inductor. And then for what they call it, B12 is going to become a resistor. You can see it here. So it's going to be, this one is going to be R12. And then next, you know, these three share the same velocity. So it's going to be capacitor C2. Then here is going to be the spring, which is I think L1. No, I know. L2 actually. Then the damper is R2. So this is going to be a system. Now to write the equations, I'm going to use KCL, sum of your notes here. I don't know why I awkwardly put it there. So it's going to be a sum of current entering into the node is equal to sum of current exiting the node. So in this case, we're going to have the sum of current entry that needs I of t plus current across a capacitor is giving us C1 dV1 over dt plus this is going to be V1 over minus 0 over R1. So it's going to be V1 over R1 equals to the current here is going to be V1 minus V2 all over R12. Then for the inductor is going to be V1 minus, actually no, then for the inductor is going to be 1 over L integral V1 minus V2 dt. That's for the first equation. Then for node 2, this for node V1. Then for node V2 is going to be sum of current entering into this node is the sum of current exiting the node, right? So in this case, it's going to be V1 minus V2 over R12 plus 1 over L integral V1 minus V2 dt. That's the current leaving this node at this point. Then the ones that are exiting is going to be equals to um, C2 dV2 dt plus 1 over L2. This plus 1 over L1. 1 over L2 integral V2 minus 0 because it's a reference to ground dt plus V2 over R2. So this is simply going to be another equation. Let me do for the mesh. For the mesh, you simply go around the loop. So it's going to be minus E of t. I like to take the first sign there. Voltage will drop across there. So it's going to be plus L1 di over dt. This is the formula for voltage across an inductor. Plus R1 I1. We are familiar Ohm's law. Plus R1 to I1 minus I2. Please, I'm trying to be writing your t in brackets. Plus 1 over C 1 integral I1 minus I2 dt equals to 0. So that's just for the first loop. Because these two are in between two loops. It's going to be I1 minus I2. I can see it's reflective of what is here. And then for the second loop, that's loop 2, we're going to have R12 I2 minus I1 because we're working reference to I2 plus 1 over C1 integral I1 I2 minus I1, we can reference I2, so I2 comes first, plus L2 dt over dt plus R2 I2 plus 1 over C2 integral I2 dt equals 0. So this is your final answer. So these are your mesh loop equations, differential equations, and other equations. I hope you really understood. Thank you.